So far in the course, we've been looking at the basics of functional programming in Haskell, and we've illustrated each of the concepts that you've been learning about with some small programming examples. So what we're going to do today is tie all of these ideas together with a larger example of programming in Haskell, and what we're going to be looking at is something called the countdown problem, which is actually one of my favorite lectures on the course. So as we often do with these things, we're going to start off with a simple question. So what actually is Countdown? So Countdown is a very popular quiz program which has been running on British television since 1982. So it's been running for many decades now. It was actually the first program ever to be broadcast on Channel 4 in the UK. It's actually based on an original French program, and I'm not even going to try and pronounce this here, but this basically means the numbers and the letters. And if you've ever seen the show, you'll know that there's a bunch of different games on it, and one of the games is a numbers game that we are going to refer to as the countdown problem. And what we're going to be doing today is seeing how to write a highly efficient program to solve the numbers game from the countdown quiz program. So I'm going to introduce you to the problem by means of a simple example. And it's a numbers game, and you're given typically 6 numbers to start with. So in this example, we have 1, 3, 7, 10, 25, and 50. And I'm going to call those the source numbers. And then the name of the game is that you've got to use these numbers to build a simple arithmetic expression whose value is a particular target. So in this case, the target number is 765. And you're allowed to use the 4 standard arithmetic operators, so addition, subtraction, multiplication, and division. So this is the name of the game. You're given 6 source numbers, you're given the 4 arithmetic operators, and then the name of the game is you've got to construct an expression whose value is a particular target, such as, for example, 765. So there's some further rules on the game, which I will just talk you through very briefly. So the first rule is that all of the numbers which you're given and all of the intermediate results that you use along the way must be so-called positive natural numbers. So this is just a fancy way of saying 1, 2, 3, etc., etc. So in particular, if everything's got to be a positive natural number, you're not allowed to use negative numbers at any point, you're not allowed to use 0 at any point, and you're not allowed to use proper fractions. So just to emphasize this point, if you did something like 2 minus 1, that will be fine as an expression because 2 minus 1 is 1, which is again a positive natural number. But if you did 1 minus 2, that would not be fine as an expression because the result is minus 1, and that's not a positive natural number. And similarly, if you do a division, you need to be careful. So for example, 4 divided by 2 would be fine because the result is 2, which is a positive natural number, whereas 2 divided by 4 would not be fine because the result is a half, which is a proper fraction, which is not allowed. The second rule of the game is that each of the source numbers can be used at most once when you're constructing the expression. So for example, if we look at the 6 numbers here, we have a 1, 3, 7, 10, 25, and 50. We can use any of these numbers, but we can only use it at most once. So for example, we have a single 10 here. So if we want to use 10 in an expression, we can only use that once. But we actually see we have a 3 and a 7. So if we wanted to make another 10, we could just add the 3 and the 7 together to make a second 10. But basic rule of the game, you're given these 6 numbers and you can use each of them at most once. If you're familiar with the television show, you'll know that there's some other rules which are adopted to make the problem practical and interesting for people to play on a TV show. So for example, you only have 30 seconds to solve the puzzle, and there's some constraints about how large the numbers can be and how large the target can be. So for example, I think the target number is always 3 digits. But here we're writing a computer program, a Haskell program, to solve the puzzle, so we don't need to worry about these rules which are imposed for pragmatic reasons, so we won't worry about any of these. So if you're watching this video in your own time, you might like to actually pause it at this point and see if you can solve this particular instance of the countdown numbers game. So try and construct an expression from these 6 numbers using the standard arithmetic operators that gives a result, which is 765. So here is one possible solution to this puzzle using these given numbers. So what I've done in this example is I've taken the 25 and the 10 and subtracted one from the other, and I've got 15. And then I've added the 50 and the 1 to get 51. And if you multiply these two numbers together, then you get 765, which is exactly the solution or target that we're looking for. You can ask yourself, well, how many solutions are there in general? So typically there are many different solutions for a particular instance of the problem. So if you work out all the cases for this particular example, you'll find actually there are 780 different solutions for this particular instance of the problem. And of course, many of these will be quite similar. So for example, if you look at the expression above, if I took the 50 plus 1 and I flipped around the addition and I did 1 plus 50, that would be a very similar expression. All I've done is use the commutativity of addition, and that would still give 765. And similarly, I could swap the two sides of the multiplication because multiplication is commutative, and that would give the same answer as well. So many of the solutions in the solution space, in this case 780, will be quite similar, and actually we're going to come back to this point later when we try and increase the efficiency of the program which we're going to be writing. So the last point here on the slide is, are there problems with no solutions, or does every countdown problem actually have a solution? And the answer is no. So for this particular example, if you change the target number to 831, this actually gives an example which has no solutions at all. It doesn't matter how hard you try to combine those 6 numbers using the arithmetic operators, it's completely impossible to reach the target 831. So what we're going to do now is think about how to write a Haskell program which will solve the numbers game. To kick things off, what we're going to do is think about how to represent and how to evaluate simple arithmetic expressions. So what we're doing in this slide is, at the top, we're declaring a data type to represent the 4 arithmetic operators. So this is extremely simple. We're declaring a data type called op, and it's got 4 constructors: add, sub, mul, and div, and these simply represent the 4 standard arithmetic operators. So they're nullary constructors, they don't take any parameters. Then what we're doing at the bottom of the slide is we're defining a function which allows us to apply an operator to 2 integer arguments. So it's giving a meaning or semantics to the 4 constructors for the op data type. So apply is a function. It takes an operator, then it takes 2 integer values. It's a curried function, and finally it's going to give us back an integer result. And the definition for the apply function is entirely straightforward. If you apply, for example, the add operator to 2 integers x and y, then you simply add them together. You do a similar thing for subtraction and multiplication. And then the only thing to watch out for is in the division case, when you divide x by y, you're using integer division, so that's div. And I've converted the div function into an infix operator by using the little backquote syntax that we learned about earlier on in the course. So the next little helper function we're going to define is going to decide if the result of applying an operator to 2 positive natural numbers is another positive natural number. Because as we've seen, when you apply an operator to 2 such numbers, you may actually end up with a negative number, you may end up with 0, or you may end up with a proper fraction. So this little function is going to check whether applying an operator is actually valid from the point of view of the rules of the game. So valid is a function. It takes an operator as its first parameter. It takes 2 integers as its second and third parameter, and these will be positive natural numbers. And then it gives back either true or false, depending on whether, if we were to apply the operator, we would get a positive natural number as the result. So let's have a look at the cases. So the first case for addition is entirely simple because whenever you add two positive natural numbers together, you get another one. So for example, if I do 1 plus 2, I get 3, and in general, whatever two natural numbers you add together, you'll always get another positive natural number. So the first case says if you apply the add operator to two integers that you don't care about, so I've used the wildcard pattern here, then that's always going to be successful, so we just give back the result true. And it's exactly the same in the multiply case. That's the third case. If you multiply any two positive natural numbers, you will always get another one, so we can simply return true in that case. So the interesting cases are subtraction and division. So the case for subtraction says if you're trying to do a subtraction, x minus y, what the definition says is that's only valid if x is strictly larger than y. So why is this the case? So for example, if I wanted to do 2 minus 1, that would be fine because 2 is strictly greater than 1, so I know that the result, which is 1, is going to be a positive natural number, whereas if I tried to do 1 minus 2, then this case would fail and we would actually get back the result false, because in this case the first number is not strictly larger than the second. So all the second line is saying is subtraction is only valid if the first number is strictly greater than the second. And then the final case for division is we need to be careful here because, for example, if we do 4 divided by 2, that's fine because we get 2. If we did 2 divided by 4, that's not fine because we end up with a proper fraction 1/2. So the trick here in the division case is we just check if when we divide x by y and look at the integer remainder, then that had better be 0. So mod is the function that does an integer division. It uses integer division of x divided by y, and it gives you back the remainder. And if that remainder is 0, then you know that you've actually done a proper division and you haven't ended up with a proper fraction. So nice, simple 4-line declaration or definition. So finally, what we have at the bottom of the slide is we're defining or declaring a recursive data type for arithmetic expressions. And this is very, very simple. So an expression can either be a value which has an integer parameter, so we could write something like val1 or val2, or we have the application of an operator to two sub-expressions. So for example, we could apply an add operator to two sub-expressions. So it's a simple recursive data type. It's got one non-recursive constructor val, which takes an integer parameter, and then we've got a recursive constructor app, which takes an operator and two sub-expressions. So a very simple example of using this data type declaration, if I wanted to represent 1 plus 2, then that would be very straightforward. I would write app, APP, and then I would write the add operator, ADD, and then I need an expression which represents 1, which is simply val1 in brackets, and then an expression which represents 2, which is simply val2 in brackets. So now that we have a way of representing arithmetic expressions, we can think, what does it mean to actually evaluate one? Because that's the important thing in the game. We want to construct an expression which evaluates to a particular target number. So what we're going to be doing here is we're defining a function that returns the overall value of an expression provided that that value is a positive natural number. So this is taking account of the idea that evaluation may fail because we could end up with a negative number, we could end up with 0, or we could end up with a proper fraction. So a key idea in this function is going to be how do we manage the representation that this function could fail. So we can see this already just by looking at the type for the function. So if you look at the blue box, the type says that eval is a function and it takes an expression as input and then it's going to give back a list of integers as its result. And you might think, well, why are we giving back a list of integers? We only want a single number coming out of the evaluation function. But the idea is that we're going to use the list result to represent the idea that this function could fail. So if you look at the callout box at the bottom, it says this function is either going to succeed and return a singleton list, so that's a list with one number in it, which will be the successful result of evaluation, or this function is going to fail and it's going to return the empty list. So if we return the empty list, that means that the result would have gone outside the space of positive natural numbers, and it would be either negative, 0, or a proper fraction. So this is actually a very common way of representing success in failure in a language like Haskell. So you return a list and you return the empty list if the function fails, and you return a list with one thing in it, or a singleton list if you want to be fancy, if the function succeeds. So now we can actually look at the definition itself and see how it works. So an expression has two ways that it can be formed. It can either be a value, which has an integer parameter, or it can be the application of an operator to two sub-expressions. So we're going to use pattern matching here to define the function, and of course it's going to end up being a recursive function. So let's look at the base case for the definition. So we're evaluating a value n, and what do we do? Well, we could just have defined this using an if-then-else. We could say if the number is greater than 0, so it's a positive natural number, then I just put the number into a singleton list by writing square brackets around it, else I return the empty list. But actually there's a nice little trick with list comprehensions, which you can see here in the first line, which lets us write this a bit more concisely. So we have a list comprehension here where we're returning the list that only contains the value n, provided that n is greater than 0. So this is an example of a list comprehension which doesn't have any generators. All it's got is a guard which is checking is n greater than 0. But this is precisely equivalent to the simple if then else, which I just mentioned, but this is a bit more concise. It only returns the value n sitting in a list on its own, provided that n is greater than 0. Then we can move to the recursive case. So in this case, the pattern matching says we're applying an operator O to two sub-expressions L and R. And then what do we do? Well, if we look after the vertical bar, the such that on the right-hand side, there's three components. There's two generators, one for x and one for y, and then we're checking whether something is valid in the third line. So let's look at these three components after the vertical bar, one at a time. So what we're doing first is evaluating the left sub-expression L recursively, and if that succeeds, we're going to recall the resulting number x. Then we're going to, in the second step, we're going to recursively evaluate the right sub-expression, and if that succeeds, we're going to recall the resulting number y. And then finally, in the third part, we're checking, is it valid to apply the operator O to those two numbers x and y? And if all three of those things succeed, then what we're going to do in the list comprehension is actually apply the operator O to the two numbers x and y to actually give us the final successful result. So what we're actually doing here is leveraging the power of the list comprehension machinery to manage the fact that a number of different things could fail here. So the evaluation of L could fail, the evaluation of R could fail, and the validity check could fail as well. Any one of those things or all of those things could fail, and we don't need to worry about that. The list comprehension machinery will deal with all of that behind the scenes for us. So we just focus on the essential idea. If you want to evaluate an application, you evaluate the left part, you evaluate the right part, check is it a valid thing to do, and then you actually build or apply the operator to the two numbers to give the final result. So this is a bit more of a sophisticated example of a list comprehension than we've seen so far in the course. So you might want to pause at this point if you're watching the video on your own and just make sure you understand actually what's going on here. But the basic idea is we're returning a list to represent that the evaluation function could potentially fail, and we're using the list comprehension machinery to manage the kind of propagation of failure automatically for us. So before we try to think about actually solving the problem, we're actually going to specify or formalize what it actually means to solve the problem. So in order to do this, we're first of all going to define a couple of helper functions. So the first function is called choices, and it's going to return a list of all possible ways of choosing 0 or more elements from a list. So let's look at the little example at the bottom of the slide. So here I'm applying the choices function to the list 1, 2. So it's only got 2 values in the list. And what it's going to give me back is all possible ways of choosing 0 or more elements from that list. And as you can see on the slide here, there's 5 different ways to do that. I could either choose 0 elements from the list, which would just give me back the empty list. There's one way to do that. I could choose 1 element from the list, and there's 2 ways to do that. I could either choose the 1 or the 2, and then I could choose 2 elements from the list, and there's 2 ways to do that. I could either choose the 1 and the 2, or the 2 and the 1. So this is why you get 5 possible choices back for this particular input list. Then we can look at the type of the function. So choices takes a list of things of type A and gives back a list of things of type A. So you might be thinking, well, what possible relevance is the choices function? And it's going to be relevant because when you are trying to solve the countdown numbers game, you can use any of the 6 source numbers in any order. And the choices function is kind of implementing that in a formal way. If you gave the choices function the 6 input numbers, it would give you all possible ways of choosing 0 or more elements from that list of 6 numbers. It's an interesting exercise to try and define this function for yourself. I'm not going to show you the definition here. I really want to focus on the concepts in today's lecture, so I'm not going to show you the definition of absolutely everything. So this is one of the functions where I would challenge you as an exercise to try and define this function for yourself. And as usual, there's many different ways that you could do this. So the second helper function we're going to use to help us to formalize what it means to solve the countdown problem is a simple function that's going to return a list of all the values which appear in an expression. So for example, if I had an expression like 1 plus 2, then it would just pull out the numbers 1 and 2, because these are the fundamental values in the expression. So the values function has type expr to list of integers, exactly as you'd expect, and it's got a very simple 2-line recursive definition. The first case, the base case, says if you extract the values from an expression which is already just a value, val of n, then all you do is forget about the val constructor and just put the underlying number n into a little list on its own. Very simple base case. Then the recursive case says if you want to extract the values from an expression which is an application of any old operator, so we don't care what the operator is here, so we use the wildcard pattern to match on it, and we have a left sub-expression L and a right sub-expression R, then all we're going to do is recursively compute the values in L, and that will give us a list of integers. Recursively compute the values in R, and that will give us a list of integers, and then we've got 2 lists of integers, and we just append them together using our old friend, the plus plus operator. So using all of these helper functions that we've now defined, we can actually define what it means to solve the countdown problem for a particular instance. So what we're doing now is deciding if an expression is a solution to the problem for a given list of source numbers and a given target number. So let's understand the components of the solution function at the bottom of the slide. So let's look at its type first of all. So solution is a curried function. It takes an expression as the first parameter, and that's going to be called e. Then it takes a list of integers as its second parameter, and that will be the source numbers, and that's the list n's. Then it takes a single integer, and that's going to be the target number, and that's n. And then it's going to give us back true or false, depending on whether that particular expression actually solves the problem for those given source numbers and target number. So how does the solution checker actually work in practice? So it's essentially a 1-line definition, but I've had to split it across 2 lines here because it doesn't quite fit on the slide. So when you apply the solution function to an expression e, a list of source numbers n's and a target number n, then it's going to check two things. So the first thing it's going to check is that the values in the expression are actually selected from the choices. So what does this mean in terms of the code here? So I'm first of all applying the values function to extract the list of underlying values which appear in the expression. So that will give me a list of integers. Then on the right hand side, I'm applying the choices function to give me all possible ways of selecting 0 or more numbers from the 6 numbers which I'm given. And then I'm applying a library function called lm, and it simply checks if a particular thing appears anywhere in a list of things. So lm is a way of checking if something appears in a given list. So putting all this together, the first line here, lm values of e of choices of n's, is simply saying, are the values selected from all possible choices from the input numbers or the source numbers. The second part of the definition is simply saying if we evaluate the expression e, then we're going to get a successful evaluation. So we're going to get a singleton list, and that value in the list had better be the target number. Okay, so the first part of the definition is saying, are the values which appear in the expression legal ones? So we're using each of the source numbers at most once in any order that we like. And the second part says, when you actually evaluate the expression, do we actually get a successful result, which is the target number that we want? So this, in conclusion then, is a one-line definition which checks, is a particular expression a solution to the countdown problem for a given list of source numbers n's and a given target number n. And you might be thinking, well, this function is potentially horrendously inefficient because, for example, the choices function, if you give it 6 numbers, there's going to be a very large way of picking 0 or more elements from a list of 6 numbers. But actually, we don't care about efficiency at this point because we're probably never actually going to run this function. This doesn't find a solution for us. It's just helping us to kind of understand what the problem is. This is like a specification for what it means to solve the countdown numbers game for a particular instance. Now that we've understood in a formal sense the problem that we're trying to solve, we can actually think now, how do we start to write a Haskell program which is actually going to solve it? So what we're going to do is we're going to start simple. We're going to implement quite an inefficient approach to solving the problem, which we're then going to improve in a couple of steps. And our first approach is going to be based upon the idea of simple brute force searching. We're going to be essentially trying all possible expressions and see if we can find any expressions which actually solve the problem for us. So in order to do this, we're going to define a couple of helper functions. And the first helper function is going to return a list of all possible ways of splitting a list into 2 non-empty parts. So again, let's have a look at the example first of all to understand what's going on, and then we'll have a look back at the type. So at the bottom of the screen, we have an example. We're splitting the list 1, 2, 3, 4 into 2 non-empty parts in all possible ways. So it turns out that there are 3 ways to split this list. We could either split the 1 off and then have the 2, 3, 4. So that would give us the first pair in the output. Or we could split the 1 and the 2 off and then have the 3 and the 4 remaining, and that would give us the second pair. Or we could split the 1, 2, 3, and that would give us the 4 remaining. Okay, so it's taking the list 1, 2, 3, 4 and giving us all possible ways of splitting it into 2 non-empty parts. So then we can just have a quick look at the type to make sure we all understand what's going on with that. So split is a polymorphic function. It takes a list of things of any old type A, and it's going to give back a list of pairs of lists of things of type A. So this is again one of these functions where I'm not actually going to give you the definition for this. All the code for the countdown numbers solvers is freely available on the web page for the module, so you can have a look at the definition there. But again, I'd actually challenge you to try and define this function for yourself. And as usual, there's many different ways you could do this. Maybe the simplest way is to do a take and a drop within some kind of list comprehension. So that's a bit of a hint about about how you could define the split function. So the second helper function I'm going to define is actually what I would call the key function in this lecture. This is fundamentally the function that's going to ultimately be the way in which we're solving countdown numbers games today. So what this function is going to do is it's going to return a list of all possible expressions whose values are precisely a given list of numbers. So for example, if you give this function the list of numbers 1, 2, 3, 4, it's going to build you all possible arithmetic expressions whose values are precisely 1, 2, 3, 4 in exactly that order. Okay, so let's have a look at the different parts of the definition of the function. So the type, first of all, is very simple. Exprs takes a list of integers as its input. That's the values which we want to appear in the expressions. And then it's going to give me a list of expressions as its output. And again, those expressions will have the input numbers as the values of the expression in precisely the same order as the input list. So then we can look at each of the parts of the definition one by one. So there's a couple of base cases which are very, very simple. So the first base case says, if you give me no numbers, then I can't build you any expressions. So applying the exprs function to the empty list of input integers simply gives me back the empty list of expressions. The second base case says, if you give me one number, one integer value n, then there's only one expression which I could build, and that's simply the value n. So that's, again, a very simple base case. Then we come to the interesting case, which is the recursive case. So we know at this point that the input list ends is going to have at least two numbers in it, because the empty list case and the singleton list case are covered by the first two equations. So ends is going to be a list with at least two numbers in it, and then we're building a list of expressions using a list comprehension on the right-hand side. So there's four components to the list comprehension, so we'll look at these one by one. So first of all, we're calling the split function on the input list ends, and that's going to split it into non-empty parts in all possible ways. So we're considering all possible pairs, L's and R's, which are obtained by splitting the input list into non-empty parts. Then what we're going to do in the second step is we have another generator. We're going to consider recursively all possible expressions which we could build over that left list, L's. And we'll consider each possible expression L one at a time. Then we have another generator that says we're going to recursively call the exprs function on R's, and then we'll be considering each of the resulting expressions R one at a time. And then finally, we're going to have a little helper function called combine, which is going to take each of those resulting expressions, L and R, and is going to combine them in all possible ways using the four different arithmetic operators. So just to summarize again what's going on, what we're doing in the first line is we're splitting the numbers up into two non-empty parts in all possible ways. Then in the second and third lines, we're generating all possible expressions over each of these lists recursively. And then in the final line, we're going to use a little helper function called combine, which is going to combine these in all possible ways to give a list of resulting expressions. So again, this is one of these kind of slightly more sophisticated list comprehensions. If you're watching this video on your own, you may want to pause this and kind of think, do you really understand what's going on here? And maybe also try writing this function for yourself. Before we move on to defining our first solution finder, we need to complete the definition for the exprs function by defining the little helper function called combine. And combine is entirely straightforward. It simply combines two expressions using each arithmetic operator. So there's four of those, so it's going to give you a list of four resulting expressions. So how does it work in practice? Well, combine, you give it an expression called L, you give it another expression called R, and we have a list comprehension on the right hand side, and we're simply having a generator where O, an operator, is selected from the list of four possible operators. So addition, subtraction, multiplication, and division. And then we're forming an application of one of those four operators to the two sub-expressions L and R. So entirely straightforward. one-line little list comprehension. So now what we have at the bottom of the slide is our first solution finder. So what this function is going to do is return a list of all possible expressions that solve a particular instance of the countdown problem. So let's have a look at the type first of all. So solutions is going to be a curried function. Its first parameter is a list of integers. That's going to be the 6 source numbers. Its second parameter is a single integer. That's going to be the target number. And then it's going to give us back a list of all possible expressions that solve that particular instance. So this is a very nice function. It's not just going to give us back one solution. It's actually going to give us back every single possible solution. So now let's look at the definition. So the header for the definition says solutions. You give it a list of source numbers, n's, and you give it a target number n, and then it's going to build you a list of expressions e, which solve that problem. So how does it actually do it? Well, we have 2 generators and 1 guard. So the first generator says we're going to compute all possible choices from the source numbers n's. So that's all possible ways of selecting 0 or more values from the source numbers n's. And we're going to consider each of those choices one by one, and we're going to call those n's prime. In the second line, we have another generator, and we're going to call the experts function, and that's going to compute for us all possible expressions whose values are precisely that list of numbers n's prime. And then we'll consider each of those expressions one at a time, and then in the final line, we have a simple guard which simply evaluates the expression e and checks is the result successful, and actually is it the target number n. Okay, so just to repeat what's going on, in the first line we're computing all possible choices over the source numbers. Then in the second line we're computing all possible expressions over each of those choices. And then in the final line we're actually checking, does it actually solve the problem? Does it evaluate the expression e to give precisely the number n that we're looking for? So this is our brute force solution finder. So of course we're computer scientists, so we want to know how fast does this actually run, so we can do some simple testing. So when I was testing this, I was running it on a 2.8 gigahertz Core 2 Duo with 8 gigabytes of RAM, half decent machine. I was running it on a particular version of the Glasgow Haskell compiler, and I tried it out quite a few times on this particular example here. So this is the example we had right back at the start of the lecture today. The source numbers were 1, 3, 7, 10, 25, and 50, and the target number was 765. And in this case, it managed to find one solution very quickly in about 1/10 of a second, and it managed to find all solutions. I think there was about 780 of them or something like that. It managed to find all solutions in just over 12 seconds. So this is nice. It's managing to solve the problem completely for us, finding one solution very, very quickly and all solutions in about 12 seconds. But actually, if you think about it, 12 seconds is a bit slow. I mean, many times on the show, people can solve this problem very, very fast and find a solution within 30 seconds. So a kind of decent machine, such as this one, which I was using here, it should actually be able to perform much, much better. And actually you might think, well, maybe there's a small number of solutions for some particular countdown problems, and maybe the solution is right near the end of the search space, and when I press return on my machine, I don't really want it to take as long as 12 or so seconds to find one solution. So maybe I need to think a bit harder about how to make this go actually faster. In this case, the key to doing better is to think more deeply about the problem domain. And the observation we can make is a simple one. Many of the expressions that are considered by our brute force solution finder will typically be invalid. And what I mean by invalid is that they fail to evaluate successfully to give a positive natural number. They either end up going negative at some point, going to 0, or producing a proper fraction. So if you run some simple statistics on this, for our example numbers game that we've been thinking about, only around 5 million of the 33 million possible expressions that you can generate over the 6 source numbers are actually valid. So this brings us to the bottom bullet point on the slide, and the idea is that we may be able to combine the generation of expressions with the evaluation of expressions to allow the earlier rejection of invalid expressions. And this is an example of what's called program fusion, combining two programs together. So at the moment we have a generate and test approach to producing solutions. We generate candidate expressions using the express function, and then we test to see if these are actually valid solutions using the evaluation function. And these are two separate functions. One is feeding its output into the other. And the idea of program fusion is maybe rather than doing these two things separately, rather than generating expressions and then evaluating or testing them, we could combine these two functions together and actually end up with a more efficient solution finder. So how do we fuse these two functions together? So what we're going to do first is define a new type called result. So a result for us is going to be a valid expression, so one that evaluates fine. It's going to give us a positive natural number, and we're going to pair that expression with its resulting integer value. So a result is just a valid expression paired with its actual evaluated value. And now we can kind of specify what we're trying to do. What we'd like to do is define a function that fuses together the generation of expressions using the express function and the evaluation of expressions using the eval function. So the definition of the function results at the bottom of the slide. This doesn't improve efficiency yet. We haven't fused anything together, but it kind of explains what we're trying to do here. This is a kind of specification that we would like to implement in a more efficient way. So what results does is it takes a list of integers and it builds you a list of all possible results over those integers. And how does it work? Well, it simply applies the expressions function to generate all possible expressions over those input numbers. And then it's going to check, call the eval function to check does that successfully evaluate, and if it does, we'll call the result value n, and then we'll pair up e and n. Okay, so this is the problem we're trying to solve. We would like to have a function called results which has this behavior but actually fuses the expressions function and the evaluation function together. So rather than doing this kind of generate and test approach with two separate generators here, we're actually wanting to do this in one function definition. It turns out to be very straightforward to actually realize this behavior in practice by defining the results function recursively. So here's the definition for it, and it looks very similar to the express function, except that this function is returning results, which are pairs of an expression and its successful value, rather than simply returning expressions. But the definition is pretty much the same as the previous one. So let's look at the two base cases first of all. So the first base case says, if you give me no numbers, there are no results. The second base case says, if you give me an input list with one number, then there's only one result. So the expression is simply going to be val of n. Its resulting value is simply n itself. And then we have a little guard in here just to check that that number is actually greater than 0. Because remember, a result must always be a positive natural number greater than 0. Then we have the recursive case. So n's will be a list with at least two numbers in it. And we proceed in exactly the same way as we did in the express function. We split the list into two non-empty parts, l's and r's. We recursively are going to compute the results over L's and compute the results over R's. And then we're going to combine the results together using a helper function. And the only real difference in this recursive case is the helper function combine prime now has a different type. It's combining results. So it takes one result here called Lx and another result called Ry, and it's going to combine those two results to give back a list of results. So then we need to think, how do we actually define this new little helper function? Well, this is quite straightforward. It looks like a jumble of symbol on the slides here, but it's actually a one-line definition which is very straightforward to understand. So what combine prime is doing is it's taking one result value L comma x, so that's a valid expression L and its value x, and then we take another result value r comma y, so that's a valid expression r, and its result value y. And then what we're going to do in the body of the list comprehension is we're going to consider each of the 4 arithmetic operators one at a time. So O is going to range over addition, subtraction, multiplication, and division. And then we have a simple guard that checks, is it valid to apply that particular operator to the 2 resulting positive natural numbers, x and y. And if that is valid, we're simply going to compute the result. And the result is obtained by simply applying the operator to the expression L and R. And then we simply apply the operator to the 2 resulting numbers x and y. So again, it looks like a jumble of symbols at the top of the slide, but it's actually a very simple one-line definition using a list comprehension. So what this gives us now is a new way to solve the countdown problem, or to solve particular instances of the countdown problem. So what we have at the bottom of the slide now is our second solution finder. So I've called this solutions prime to differentiate it from the first one, but it has the same type as before. It takes a list of integers, which is the 6 source numbers. It takes a single integer, which is the target number, and it's going to build you a list of all possible expressions which solve that particular problem. So how does it work? Well, suppose the 6 numbers are the list n's and the target number is the value n. Then what are we going to do? Well, we have a list comprehension with 3 components. First of all, we're going to compute all possible choices over the 6 source numbers, and we'll consider each of those choices n's prime, one at a time. Then we're going to call the results function on each of those choices, and that will give us a expression e, which evaluates successfully, and it will give us its resulting value m. And then all we need to do now is check, is that resulting value m for the expression e, is it actually equal to the target number n? So we have a little guard, it's m equal to n. If it is, then we will keep the expression in our solution list. So this is our fused program. We're no longer generating expressions and then testing them separately to see if they evaluate successfully. We're kind of doing that at the same time using the fused function called results. So again, now we can ask how actually fast is this in practice. So if we try it with our example again, 1, 3, 7, 10, 25, and 50 are the source numbers. 765 is the target number, then this time around we're now finding one solution in about 1/100th of a second, and we're finding all solutions in about 1.3 seconds. So this is about 10 times faster in both cases. So this is actually a very nice example of program fusion. A lot of my research is actually to do with program fusion. It's the idea of making programs faster by combining 2 programs which were running in sequence, actually combining them into one program which achieves the same result but in a much more efficient way. So we see this here. We've combined the generation of expressions with testing them to see if there are solutions, and actually we've ended up with a solution finder which is about 10 times faster than the one we had previously. So at this point now, we could actually stop if we wanted to, because we already have a highly efficient program for solving the countdown problem. But actually we can do better with a very simple observation, which we essentially already made right back at the start of the class today. And the observation is that many of the expressions that we generate will be essentially the same as other expressions using simple arithmetic properties. So here's a couple of examples of the kind of properties we might consider. First of all, we have a commutativity property, which says that x times y is the same as y times x. And then we have a simple identity property, which is saying that x times 1 is the same thing as x. And the idea here is that if we exploit such properties, this would considerably reduce the search space and also the solution space. So it turns out that there's a very simple trick to exploiting these properties, and that is simply to modify the definition of the valid function. So here's the definition which we had right back at the start of the class today. So what valid does is you give it an operator, you give it two positive natural numbers, and it decides, returns true or false, depending on whether if you were to apply that operator to those two numbers, you would get another positive natural number. And it turns out to be very straightforward to exploit these commutativity and identity properties just by making some simple changes to the definition of valid. So the first change we're going to do is, rather than saying it's always okay to add two numbers x and y together, we replace the true here by x being less than or equal to y. So now we're going to say, for example, adding 1 and 2 is okay because 1 is less than or equal to 2, but adding 2 and 1 is not okay because 2 is not less than or equal to 1. We can do the same kind of thing for multiplication. We can take account of the commutativity of multiplication by saying that we're only going to allow two numbers to be multiplied if the first one is less than or equal to the second one. So multiplying 1 and 2 is fine, but multiplying 2 and 1, we're going to say that's no longer fine. We can also, at this point, take account of some simple identity properties as well. There's no point in multiplying if x is 1 or y is 1, so we can put two simple constraints on there as well. And similarly, when you're doing a division, there's no point in doing a division if the y component is actually 1. So we can put a little test for that on as well. So these simple changes here, we've made 5 changes to the definition. These take account of, in a very simple way, some commutativity and identity properties for us. So finally, we can wrap things up now by thinking how fast is our solution finder if we use this new version of the valid function, which takes into account these simple properties. So I'm going to call the function which finds solutions now, solutions double prime, and we're going to run it on the same example as we had before. And this time around, in terms of reducing the size of the search and solution space, we get a significant reduction. So this time around we have about 250,000 expressions which are valid, which is about 20 times less than we had previously. And now the number of solutions has also decreased dramatically. We now have 49 expressions which solve the problem, which is about 16 times less than what we had before. In terms of actual performance, now our program, our final solution finder, solutions double prime, will find one solution in 7 1,000ths of a second, which is about twice as fast as what we had before, and it will find all possible solutions in about 0.1 of a second, which is about 11 times faster than what we had before. And actually, if you try some more experimentation, more generally, the final program which we have produced usually returns all solutions to a countdown problem in a fraction of a second and is around 100 times faster than the original brute force program which we had. So that's it for today. It's an example of a more sophisticated Haskell program which brings together lots of ideas which you've seen in the course so far. And if you're interested in having a look at this program and maybe trying it out for yourself, the program is freely available on the web page for the module. So that's it for today. I will see you again next time around.